without knowing the matrix, how can vector matrix products be computed is the question. For example, if you want to know the curvature condition, I need to know the Hessian. Now the point that I was trying to make earlier is, we obviously need to know the Hessian. If I don't know something, how can I calculate the product of that something with a vector? The point is, how I store the matrix is where the innovation lies. I need not store the matrix in a dense way. That is what it means, that matrix vector product is inexpensive if, can be evaluated efficiently as compared to storing n squared entries. So anyway, this point we will not be covering in this course because it is a point of numerical linear algebra implementation. So whoever has this doubt, just come and talk to me after class. For non-linear CG method, is there a guarantee of convergence in n steps like in linear CG? The point is that in the linear CG, where did n come from? How did n enter the problem itself? The size of A, it was n cross n, right? So now there is no A matrix in the non-linear CG method. So n steps, there is no guarantee. Even if your input vector is of length n, there is no guarantee of n steps convergence. And is it only for convex methods? It's not only for convex methods. It is for general nonlinear functions. Why can't we do a linear / quadratic approximation of the function followed by linear conjugate gradient method? Very good question. So we are trying to do, we have a nonlinear function, we find it difficult. Why don't we linearize it or make it quadratic and then do linear CG? What's the problem with that? Correct. So if I draw a complicated function like this, let's say, okay, it won't be like this, right? If I am at, let us say at this point over here, if I do a linearized approximation, I will get basically this line. So this line will help me in one small neighborhood, right? So if I am within this small neighborhood, it is approximately correct. The moment I go outside of it, again I have to update. So if I do linearized approaches, they work, and that's one legitimate way of doing it. You can be fancier, you can say, let me approximate it here by quadratic, I'll get something like this, right? So if I'm lucky enough to be close to the solution, it will work. But if I'm sitting somewhere over here, now if I fit a quadratic, then supposing I fit something like this, right, then what do? Basically the solution is go to either end and you will get minus infinity. So these tricks are used. In fact, what we will see later in Quasi-Newton methods, some kind of tricks like this are done. But what we have is the nonlinear method, which is a little bit more general than restricting yourself to first order or second order model. How are we going to approximate the Hessian matrix? We will come to that today. Okay. So we are talking about Newton methods. Okay, so the general recipe of the Newton method we saw last time, that I am going to write the search, the direction as something times gradient of function. What is that something? Not beta, beta would be dangerous, B. Right? Some matrix BK inverse, and BK was what? Right, so now BK could be either, depends on the context. In the Newton method, BK was equal to Hessian, and in Quasi-Newton method, approximation of the Hessian. So this common notation will cover both methods. When you see this, don't immediately conclude that it's Newton or Quasi-Newton. You have to ask further what it is. Okay. Now, what I'm going to do is I'm going to show you a small property of convergence. We should have some proof that this method converges, right? In the steepest descent method, we had shown that the method converges. In the conjugate gradient method also, we had shown that it converges, in fact, in at most n steps. So similarly, there is going to be some proof of convergence. The proof techniques are similar to what we did for steepest descent. So there is nothing new really for you to see, except just a reapplication of how we will do it. So we'll look at that. Then I'll show you what the rate is. The rate is quadratic, which is why Newton methods are so attractive. Okay, and then we'll come to these quasi-Newton methods, which are also very nice. Okay, so that's roughly what we're going to do. So do you remember this Zooten-Jix condition? We had done this quite a while, about a month ago, right? This was when we were trying to prove that the steepest descent or any line search method converges. So the Newton method, the way we wrote it, is also a line search method. The only difference is the direction pk is different from steepest descent. Okay. So this was also, I think, one of the last questions of your quiz. I had something like this. So this was telling us how f of k was reducing in terms of this running summation, right? And we had said that if you look at what is inside over here, this term will always be positive, obviously, right? So this summation j is equal to 0. As j tended to very large number of iteration steps, what did we want for the method to converge? This term cos theta j times grad f should be tending to 0, right? Why do we want it to tend to 0, by the way? Can someone answer in plain English? What if it didn't tend to 0? Then fk would become unbounded. Even as I'm going to infinite terms, I'm continuously adding something finite. That would mean that fk would become unbounded. On the other hand, we started the whole discussion by saying that it's common sense only to optimize functions which are bounded from below. They don't go to minus infinity. For example, if someone says optimize log of mod x, find a minima of mod of log of mod x. We know that as x tends to 0, this thing goes to what? Minus infinity. So it's nonsensical to optimize it. So we start off by saying let's deal with functions that are bounded from below. So that means this should tend to 0 for bounded functions. Okay. Now for this to tend to 0, what are the two possibilities? Either the first term is 0 or the second term is 0, obviously, right? So either cos theta j tends to 0 or norm of this thing. Which one do we want? If you want the method to converge to a stationary point, what do we want? The second guy, right? The second guy had better be true. Okay, why? Because stationary point is grad f equal to 0. This is why we want this. Straight away, the implication therefore is that this cos theta term therefore has to be strictly greater than 0. Otherwise, it's getting multiplied by, my stationary point condition may not hold. So cos square theta j should be strictly greater than 0, okay? Not greater than equal to, but strictly. Okay. So in the case of the Newton method, what ends up happening, it's quite easy to show, is that there is a certain condition on the Hessian. Okay, so there is a condition on the Hessian, for this. By this I mean And that condition is that the condition, it's kind of funny to say it, the condition is that the condition number of the Hessian should be, should have a bound. It should not be arbitrarily large. Okay, so that condition is, so kappa of bk is less than m. Okay, now we'll show why this is the case. Okay, this is the condition. That kind of, before we get into some algebraic proof for this, can you think of an intuitive reason why this makes sense? Why should we have a bound in the condition number? What is condition number doing after all? Remember what was, it's amplifying the errors, right? So obviously if the amplification goes very, very large, every time you make a step in a certain direction, you're going to have some errors over here. And this is a proof of convergence. We want the method to converge. So intuitively you can expect that putting a control on the condition number is going to help us to arrive at the solution. This is a very, very rough hand wavy argument, but we can look at it a little bit more precisely. Okay, so what is, how does this lead to cos theta j being greater than or equal to 0? Okay, so let's look at the proof. Now this cos theta was the angle between what and what? This is related to what we call the descent direction. So pk and grad f, right? So pk and minus grad f, right? The gradient, the negative gradient. So cos theta therefore is the angle here minus grad f transpose pk and normalize it. Yes, so here I am using the, everywhere I have a subscript k. Okay. Now I am going to use two properties of norms to come to this result, two fairly straightforward properties of norms. So that these are, if this exists and is positive definite, supposing the matrix B or Bk exists and it's positive definite, can we say anything about square root B? Will it also be positive definite? First of all, what do I mean by square root of a matrix? Does it make sense? Right, so has anyone seen this ever written before for a matrix? It kind of looks funny, right? But what is it effectively? It is b to the power half. Now if I tell you a multiplied by a, you would say, oh, there's no problem multiplying a matrix with a matrix. So b to the power half, what would it end up being? So it's going to be that matrix which when multiplied with itself gives me back b. That's one way of looking at it, right? And there is a very simple way of writing it. So if I had the eigenvalue decomposition of b, what would it be? So if b was q lambda q transpose, then b square root would be what? Right, so the square root simply transfers over here. And you can convince yourself that if I multiply two of these with each other, what will I get? Q transpose q inside will become identity. Lambda to the half multiplied by lambda to the half will become lambda. I get back b. So this is legitimate candidate for square root b. I'm going to work with that. Okay, so this guy. Now is this guy positive definite? Clearly it's positive definite. So therefore this is also p, positive definite. Okay. Similarly, I can also talk about b to the minus half. It makes as much sense as b to the plus half. All that I have is negative 1 by root lambdas will appear in the diagonal term also, is also positive definite. The second is a property of norms, which simply says that if I have the norm of a product, this is less than or equal to norm A times norm B. This is again follows from linear algebra, we won't prove it over here. Okay. Now our search direction, I'm dropping the k for now because we are sitting at the kth iteration also. So let's just write over here, dropping k over now. P was simply minus B inverse grad f, right? This is for the Newton or Quasi-Newton method, which in other words, I can write this as grad f is equal to minus B times P. Okay. Now, what are we, the thing to keep in mind is this is the guy. And what do we have to prove? What is the end goal? I have this expression for cos theta k. What do I have to prove? It is positive, right? And I have to somehow relate it to this condition number business. Okay. Now you can see this property number 2 which I have used is going to help me in which part of this expression? Norm of A into B is less than or equal to norm A into norm B. Where can I can possibly use this somewhere, right? In the numerator, denominator, there are both places depending on how I take it. Okay. The third thing, what was the definition of the condition number? Just like the textbook definition. No, that is a more applied definition, the ratio of singular values. That's one correct definition, but there's another way in terms of matrix norms. Right. So this was the product of norm of B multiplied by norm of B inverse. Okay. And we are given that this is less than or equal to M. This is given to us in the problem. Okay. So now I'm going to take my cosine expression and notice your cosine expression, is the matrix B inside it anywhere? It's only in terms of grad f and P. So far B is not there. If B is not there, M can't enter the condition number, right? So the first trick would be to now somehow get B into the picture. Is there a nice way by which I can get B? Yes, right? Because grad f is equal to minus B into P. So that's our first clue, right? That let me at least get B into the picture, then I can put some inequalities on it. So this guy over here, I'm going to substitute and get rid of which guy? Grad f. Right? So cos theta would be equal to minus grad f would become, the minus and minus would become a plus. I have a P transpose B, look at this. B transpose, can I write it equal to B? Hessian is always symmetric because the mixed partial derivatives are sitting there, right? So then I have a P. This is the numerator, and denominator has so there is a, B into P, and then what else do I have? I have a P. So what we can do is we can take our this inequality from 2. Okay, so inequality from 2 is saying that norm of AB I can split as norm A and norm B, right? If I take it in the reciprocal, what will this be? 1 by norm A, norm B would be, right? All are positive quantities, I can do this. So if I apply this over here, I'm trying to open up this guy over here, right? So this expression over here would be, I can write it as greater than equal to something, right? This expression can be written as greater than equal to, what will I have? Numerator stays as it is. Greater than equal to, this is the guy that, this is, think of this, think of this as this. Okay, I should have written it that way. So this is greater than equal to, I'm going to get a norm B and then P squared. Okay. Fine. Now, can we simplify this numerator in some nice way? Can I write it as the norm of something, norm squared of something, for example? The hint is the square root B guy that I had introduced. P transpose B P. Can I write it as P transpose root B root BP? I can write it like that. And will root B also be symmetric? It will also be symmetric. So this guy can therefore be written as norm of root BP whole squared. Can I write it like that? Right. So I'm trying to now simplify this numerator expression over here. So what do I get? So I get cosine theta is greater than equal to, I have a norm of b to the half p squared, okay, and denominator I have norm of b and I have a norm of p squared. Okay. Now let's we are basically what we are trying to do, somehow get rid of some of these extra root b's, just have one b over there, then I can replace this condition number over there. This p itself I can write as b to the minus half, b to the half p. Supposing I write this p like this, is it correct? B to the minus half multiplied by b to the half and p, right? Now you can see what I am trying to do with this. I am going to try to split it in this way so that b to the half times p is there in the numerator and denominator. That's going to be the strategy. Okay. So let's get rid of this over here. So this can further, I'm going to write this as b to the half times p squared. This b remains over here. Okay, and now then here is where I split it open. So I have b to the minus half, then b to the half times p. This whole thing is squared. Okay, so what I did was, is the inequality still valid? I use that norm of a into b is less than equal to norm of a into norm of b. So I've used that trick a second time. Right? I wrote it like this and then I clubbed this as this is my a term, this is my b term, and then norm of a into b is less than equal to norm a, norm b. So when I go, it goes into the denominator, it reverses sign. Okay. Now can you see what what happens? Does the numerator cancel off? I have b to the half into p, norm squared is there. Is it there also in the denominator? It's also there in the denominator, right? So this guy and this guy cancels off. There is another simple enough property of linear algebra that this is equal to, you can take the square inside basically, right? So what do I get? This becomes 1 by norm b and then this becomes norm b inverse. Right? And this expression is what? This is related to our condition number, right? So it's a little bit of, it's not difficult, it's just, you know, if you know that you want to somehow get in the condition number there, I need to get b and b to the minus 1. These two have to appear together. And so I repeatedly use this norm property over here to somehow keep splitting it until I got rid of this the numerator and I was left purely with b. If I was stuck with a p somewhere, then I'm in trouble because p could be anything depending on the iteration, right? Here I've managed to get it regardless of the direction p. I only got it in terms of b. Now regardless of the iteration, if you tell me that the condition number is at max m, this condition will always be valid. That means cosine theta is always greater than 1 by m, do whatever you want. If that is the case, then if you look back over here, if this is greater than 0, that means the only way this Zutendix condition is going to work is if grad f equal to 0. And if grad f equals to 0, that means I have arrived at a stationary point. Okay. So these proofs of convergence typically will use these kind of inequalities, maybe Cauchy-Schwarz and this norm inequality, and then a whole bunch of clever algebra. The first time you see it, it looks like rabbit being pulled out of the hat. Or you see it a few times, these are a few standard tricks, nothing much to it. So this are we get this condition. Therefore, grad f tends to 0 as j tends to infinity. So i.e. Newton method converges. Again, practitioners almost, they don't care about this because it's, they care more about the rate at which convergence happens. Okay. So I'm going to state without proof that the rate of convergence is quadratic. Okay, so the rate of convergence is this is in Nocedal and Wright. I think this is theorem, or rather look at section 3.5 where they have a proof for this. Okay. So this is, as I've been saying many times, this is the reason why Newton methods are very popular, because you get quadratic, right? So quadratic just simply means that if I look at this distance, xk plus 1 minus x star, right? And this was less than equal to some constant over here, and then I have xk minus x star. So what is the difference between linear and quadratic? You're going to get a square here. Okay, so this is from quadratic. If you had linear, this would be to the power 1. So this is showing you that as I get closer and closer to the solution, this error in some sense is going to 0 at a much faster rate, right? Imagine that at step k, this guy, norm of xk minus x star was 0.1, right? In a linear method, the next iterate had to be less than constant times 0.1. But in a quadratic method, this has to be some constant times 0.01. So it is going towards 0 at a much faster rate. That's why quadratic is a huge deal, right? It's not just a scaling factor or a linear factor. It's an exponential, power 2 by which it is going. Okay, so this is the whole reason for the charm of Newton method. Any questions on this? The proof just has, some getting used to by looking at it a few times and then you master it. Okay.